What?
10 minutes. Oh.
Oh, I thought you said you like sent me 5 emails. I'm on. I only usually ignore like 4, but the 5th one I would really get to you at least. You know. I'm like, wow, it must have been really important. That's good. All right, so there's not like 300 emails in my box waiting for me. Maybe. All right, that's all right. You're like to be continued. All right, let us finish up some nuclear chemistry, which 18 they say. I don't know. I know that because I said no to 19, so I know that's not 19. All right, so last time we got into, towards the end there, we got into some nuclear binding energy. And remember, binding energy is the difference between the mass of the nucleons, which are protons and our neutrons, and the mass of the isotope that's going to be kind of converted into energy. That difference in mass is the mass defect. And you can calculate the mass defect by basically taking the number of protons plus the number of neutrons there are, times obviously the atomic mass of both of those guys. You subtract it from the atomic mass of the isotope, and that will give you, again, your mass defect. And at that point, you do have a couple options like we talked about. You can use Einstein's equation equals mc squared, which would require you, as we talked about, you'll end up with AMU meters squared second squared. Then you can divide it by Avogadro's number to the 26, and that will take you from AMU to kilograms, and that'll take you from kilograms meters squared second squared, which is a joule. So that's one approach. You also could use some of those conversions that we saw, which kind of shortcuts it, and like 1 mega electron volt or 931.5 mega electron volts in an AMU. And you can use the joule conversion as well. That 1.602 times 10 to the minus 13 joules is in a mega electron volt. So there's a couple different ways you can do that. Typically, we do binding energy per nucleon, and that also is a measure of stability, like we talked about. So the higher the binding energy per nucleon, the more stable it is. And out of the 3 we did last time, we hit that, I think, iron 56, which was the highest in binding energy per nucleon. And that's also the one that we saw toward the top of the graph, where we looked at sort of stability of binding energy. Any questions on that there? All right, now just to finish up a little bit of it here. So after 84, a lot of things are radioactive, and a lot of our self-made sort of particles are made by what is sometimes referred to as nuclear transmutation. You have a magnetic field, and electrical field, and basically you just kind of get a particle spinning really fast, and then you shoot it at its target. That obviously is going to make it a little upset, and usually it'll go through some type of fission sort of reaction and decay process. And these are sometimes referred to as transuranium elements, and these are all through nuclear transmutation. Here we shoot neutrons at it, alpha particles. And again, this gives us our fun names: berkelium, californium, einsteinium, all these guys. And again, that's sort of how man-made ones are made. They basically shoot particles at some stable nuclei, and they become unstable and form these sort of man-made ones. Again, a lot of them are on the bottom there of the periodic table. Speaking of nuclear fission, as we talked about, it can be spontaneous. It also can be sort of occurring via what we just talked about there. And one way you could do that is, again, you could shoot a neutron at it. And obviously it's going to hit our soccer ball here, make it a bowling pin. And it's unhappy in a bowling pin situation. So it's going to split off here into 2 new nucleuses. And we'll give off, obviously, some more neutrons in this process, and a bit of energy there. Actually, a good amount of energy will come off in this process here. And as we talked about earlier, and we'll talk about here in the next slide as well, these guys, again, can sort of kick off that reaction and keep it going. As we talked about, you get about 2 times 10 to the 13 joules of energy in a fission reaction, and that is a lot more than you get through, say, the combustion of 1 ton of coal. The comparison there is because in a nuclear power plant, they use a fission reaction to sort of do everything. And in a traditional power plant, they burn coal, basically. And that's the difference there in the energy. And you can see you get a lot more energy out of the fission reaction. Now, when we do a fission sort of reaction, you do not always get the same two guys come out all the time. So you can get a variety of sort of products that are formed, but you definitely usually will get some neutrons and some energy. This is the mass number, some of the mostly formed ones in these sort of fission reactions. But once again, it's not always going to be the same sort of products that will occur. This reaction is, again, like I said, what is used in a nuclear power plant. It is also can be used in, say, a nuclear sort of weapon. And what can happen in this reaction is what's sometimes referred to as a nuclear chain reaction. And a nuclear chain reaction is a fission reaction that basically is self-sustaining, and it will be able to kind of continue on in this process. The way it's able to do that is if you have a critical mass of, say, uranium or some type of product that or process that can go through fission, it will be enough to keep it basically self-fed. So as we just saw in the previous slide, kind of what kicks off the reaction is a neutron. And obviously the result of this is you make a bunch of neutrons, which obviously can continue to sort of react. And basically what you're doing is sort of exponentially you're growing this reaction, and it will just kind of keep feeding itself. After each time it goes through it, obviously it's releasing a lot of energy. Not only that, it's also releasing a lot of byproduct or products of those reactions, which also are very radioactive and have a very long half-life that's going on as well. Now, one way you could kind of prevent that is a non-critical sort of mass of something like uranium. And if you have a non-critical mass of it, it will not be enough to keep this reaction sort of self-feeding and self-generating. And that's sort of in a traditional sort of bomb situation here. They have a subcritical mass of uranium-235 in two different locations, the classic triangle, making the hole over here. And obviously, when this hits, you have some explosiveness there that's going to send that wedge right in there. And now you have an actual critical mass of something like uranium, and then that will keep that chain reaction going. And like I said, it's not necessarily just the blast per se, but all the products that are made obviously are not so great to be around as well, as they are very radioactive and definitely some gamma emitters, for example, beta emitters, and have very long half-lives. This is also, like I mentioned before, the sort of reaction that's used in a nuclear power plant. Our closest one is San Onofre, although I don't think they're using them anymore. They're just out there as decoration, perhaps there by the water. Um, but this is sort of a schematic of a nuclear power plant or a reactor. And all power plants sort of work the same in a sense. They basically have water, and basically they heat the water. And when they heat the water, you create steam, and steam goes out to the turbines and out to the generators, and then you get some lights, right? And the difference between sort of a traditional power plant and a nuclear power plant is kind of how they heat the water. In a traditional power plant, they burn coal, like we saw on that previous slide there, and they use the heat flue that's coming off there to heat the water. In a nuclear power plant, they use a fission reaction, the energy coming off of that to basically heat the water to create the steam that's necessary. And in a nuclear power plant, they have sort of where the nuclear reaction sort of occurs. They have fuel rods, which frankly are like eraser-sized pellets of uranium. And basically that's what's going to kick off the fission reaction. So what happens obviously is the fission reaction occurs here. They have some insulated water that gets really, really hot from that energy. And that as well will heat up this bigger picture of water. That will create some steam that again will go off to your turbines and generators and create some power. Usually these guys like to then kind of cool down the steam and kind of recycle the water, if you will, right? Because if you cool down steam, you get condensation and you get liquid water back. Also why nuclear power plants are oftentimes located near a very big body of water, like in San Onofre over there in the ocean. or if they are not located near an ocean, like in Arizona, if you ever drive down the 10 by Palo Verde, that where their nuclear power plant is, they have really big cooling towers, they call them, big things of water basically used to do that. And it keeps this sort of cycle going. So how does it not go out of control? Obviously, they keep a non-critical mass of uranium. So just in case, it should hopefully not be enough there to self-sustain that reaction and kind of go out of control. They also have what are referred to as control rods. And control rods are things that are like cadmium, kind of dipped in cadmium. And these are good neutron absorbers. And why would a neutron absorber be a really good idea in this situation? Because that's basically what starts the reaction, right? And that's what's produced. So having these control rods will kind of take a lot of those neutrons out of play and again, keep the reaction sort of under control and stuff like that. Unless, of course, you do a test and you take all the control rods out too quickly and can't put them back in, then you get some trouble. But that's the idea there. So it is sort of clean in the sense that obviously it provides that energy. You're not burning coal, but clearly you're making a lot of radioactive waste, which for a lot of years nobody wanted to dump anywhere, right? So nobody wanted to truck through their town or anything like that. So for a lot of years, these places would keep pretty much everything on site, all their waste and everything like that, because they couldn't move it. Then years ago in Vegas, they decided to dig a big hole. That's how the lights stay on there. And they started using it, I think, as well. So they started using that, I think, and kind of sending things that way. A lot of them is actually not functionable anymore in most of these nuclear power plants because it's too much to keep them up money-wise. So a lot of them just kind of sitting there, not really functioning as power plants. As I mentioned before, there's sort of pros and cons for both. Clearly, you get a lot of environmentally not so friendly things when you burn coal, not to mention how you get the coal. You got to strip down a lot of land and stuff like that to get it. And also, obviously, in a nuclear reaction like fission, you're going to create a lot of radioactive byproducts that have half-lives for a very long period of time. As you can see here, what is sometimes referred to as spent fuel is basically the result of these fission reactions and the sort of products that are made as a result of them. And the problem with that, as you can see, storage time, it's a lot of years, 10 to the 4 years, right? For storage, or 10 to the 6th or 5th years. So it creates a lot of situations, like I was mentioning before, that, a lot of situations of, where do you put it? Who keeps in track of it for all this time? And, what do you store it in for all that many years and stuff like that before it's kind of safe? So, like I said, they've started, I think, using that in Vegas a number of years ago. And kind of get rid of some of that stuff. Now, another sort of reaction is nuclear fusion, and nuclear fusion is different than fission. Fusion is basically the combination of two smaller nuclei to make a larger one. This happens at very, very super, super hot temperatures, like your vacation on the sun type of deal. So really, really high temperatures. That's why all those spy movies, right? They always want the guy that created cold fusion, right? Because you don't have to do it on the sun type temperatures. So fusion, two smaller things make a larger one at very, very high temperatures. Fission, basically one guy kind of breaks apart into two and can be starting. Radioisotopes are used in medicine, as we might have mentioned previously as well. Again, obviously, if you're going to use it in medicine, you want a smaller half-life. And they can be used for a lot of things, like sodium-24 is a blood flow tracer. Technetium-99 is used for imaging. Brain scan, iodine-123. So radioactive isotopes, just like normal elements in your body, basically behave the same way, but since they're radioactive, they basically can be found and highlighted by following the radioactivity. They do that in labs as well, just regular research labs, like if you're doing something with a protein. For example, I used to do protein with copper, and we would use copper-64 just to see where the copper went throughout the whole sort of purification process, and you could follow it based on its radioactivity. They also could use things like radioisotopes to shrink tumors. They used to implant them right into the tumor and to try to shrink them and stuff like that. And again, here you can see a bone scan here. And again, it will just highlight all the areas, obviously, where that element ends up. And it will give you sort of a visual representation of what's going on. This is a Geiger counter, which if you ever use radioactive sort of elements or isotopes. You'd probably be familiar with this. So usually if you're working with something that's radioactive, they usually will give you like a ring to wear and a badge. And every so often they develop it to make sure you're not glowing as well, right? So people used to get in trouble because they would put their lab coat on their chair and then go to lunch and just leave it sitting there all day next to the experiment. And they're like, whoa, you should really take some time off because you have too much exposure. So they usually tell you to try not to leave those things near the experiment if you're not in them. But a Geiger counter basically will test for radioactivity. It'll beep, 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 right? You should always check your shoes so you don't take anything home with you as you leave and the counter and stuff like that. If I hold this up, will the Geiger counter, will it make some noise? It will, and that's something you always hear is background radiation, especially if you're the one that's in charge of it. Oh, that's background radiation. Don't worry about it. That loud beeping is not that important. No, I'm just kidding. It shouldn't be beeping that loud, but there is always background radiation, so it will make some noise. But if it makes a lot of noise, that's not so good. As we talked about before, sometimes you do need lead, you do need gloves, obviously, depending on what you're working with. And as I mentioned before, you should always, for yourself, figure out what you're working with and make sure you understand the safety. Obviously, time is a really big factor of trying not to be around it. Obviously, is a big thing. Radiation absorbed dose, which is a RAD, is one measure of sort of the biological effects, and a RAM is an equivalent for man. And there's a quality factor there based on the type of emitter it is. So alpha particles, if you remember, don't penetrate as far into the tissue as, say, gamma rays does. So if you're exposed to gamma rays or beta rays, they're going to go further, which means you get less sort of exposure to it. It's going to cause a little bit more damage than if you're hanging out with an alpha emitter there. We get things from cosmic rays, dental x-rays, air travel. If you're living next to where they test weapons, or if you're living next to where there's nuclear waste, depending on where that is, we do get exposed to a bunch of stuff all the time. These are strawberries. Good talk. All right. Any questions on that there? All right, that is nuclear chemistry, the last part for our exam, which is 1 week from today. Yes, on chapter 18 and chapter 17, electro. And we're going to go off to 20, and that is transition metals. And dare I say it is the second to last chapter of the season, I think. Yeah, so that's good. Transition metals, we're going to talk about chemistry of transition metals, and mostly we're going to talk about coordination compounds as well and complex ions in this chapter. So the first hopefully will be a little bit of a review of transition metals and some of the periodic trends and properties of transition metals. So let's talk about some of these things that might be a 200A throwback. We'll see. So let's talk about effective nuclear charge. So that's Z effective, as you may know, or maybe not. Electrons are affected by obviously the pull it has towards the nucleus. There is an attraction between the nucleus, which is positively charged, right, and those electrons which are negatively charged. And depending on the location of those electrons to the nucleus, they may be held tighter or they may be held not as tight. And Z effective tells you basically the charge that electrons are feeling as a result of what is sometimes referred to as shielding. So for example, if we take lithium, little 1s2, 2s1 action on electron configuration day here. And lithium is number 3 on the periodic table, which means it has a +3 nuclear charge from the 3 protons. It's also got some neutrons in there, but they have no charge. So here the +3 charge is coming from the protons. It has 2 electrons here, which are referred to as core electrons, right? They are in the lowest energy level. By the way, that's what the first number means. That's that principal quantum number, right? N equals 1 in this case. We have 1 electron here on the second energy level. This is known as the valence electrons, right? Those are the outermost electrons. Those are electrons involved in bonding. And this is on the second energy level, N equals 2 in this particular case. So if I were to draw this N equals 1 situation here, and we'll kind of draw it like this, not exactly how it is, but we'll go that way with it. So when we have our electrons flying around, obviously randomly about the nucleus, we have these lower energy electrons, which are our core electrons. And frankly, they are going to feel the full brunt of that +3 charge, right? And one of the things about electrostatic attraction, which is positive and negative attraction, is the larger the charges, the stronger the attraction. So something that's a +3 and a -3 will be attracted to each other stronger than something that's a +1 and -1 sort of attraction. So these kind of core electrons, which are close to the nucleus, is going to feel really that full brunt of that +3 charge. Now, when we get to the valence electrons, in this particular case, which is this guy right here, this electron, which is our valence electron, is going to experience what is referred to as shielding. And shielding means that it is essentially shielded from the full brunt of the +3 charge that those core electrons are feeling, because those core electrons are frankly in the way and they're blocking it. So it's like, again, if you went to the movie theater and you sat down and your seat was like dead center, you're happy with it, right? And right before the movie starts, somebody comes and sits down with a big giant cowboy hat right in front of you, just shielded half of the screen, right? So that's the same idea here. So that outer electron, because it's experiencing shielding from these lower energy electrons, is not going to feel that really strong attraction. You could actually calculate the Z effective by taking the positive charge here in the nucleus, which in this case is +3 for our lithium. And you could actually just count it up to our negative charge here. We have -2 basically electrons below it. And what that outer electron is actually experiencing here is more of a +1 attraction to the nucleus. And that is a much weaker attraction than our core electrons. That is why our valence electrons, right, are the ones that are involved in bonding, because they're not being held as tightly, right? And those core electrons are not really involved in bonding or those type of activities. So when we talk about Z effective, and you look at the periodic table, it increases as you go to the right and decreases as you go down. As you go to the right, the Z effective gets larger, and that is because there's more protons, right, on the right-hand side of the periodic table. And what that does is even the outer electrons now, because there's more protons in the nucleus, will now be brought in closer to the nucleus because of that greater positive charge, even though it might be shielding a little bit, it will still have a greater positive charge. That's going to bring everybody closer. That is also why when we go to the right, the size of everybody gets smaller, right, for that effect, because it brings those outer electrons closer in because of the larger positive charge. And that's what we see here as we go sodium, magnesium, aluminum. That's going across period 3 on the periodic table. The Z effective gets much larger, and we can see the radius gets much smaller. Again, it's bringing everybody closer in together, because of even the outer electrons are experiencing this greater positive attraction to the nucleus. And again, as I mentioned, that's how it increases. And again, that's why we do see the radius, it gets smaller as you go up and to the right, and it gets larger as you go down and to the left as well. So a lot of what we're going to talk about here, especially when we get into coordination chemistry, it involves a lot of transition metals, and hopefully you remember what transition metals are. It is between group 2 and group 3 on the periodic table. These are our transition metals there. And when we talk about transition metals, right, that is the D block, right, on the periodic table. First two over here are the S block, because S could hold 2 electrons, right? 1 and 2. Over here is our P block, right? And they could hold 6 electrons, 1, 2, 3, 4, 5, and 6. And obviously this is our D, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. We'll add it in here. This is our F block down here, right? And if you count across here, 14 boxes. And that is, again, based on our electron configuration. So we're going to talk about the transition metals and a lot of the first row transition metals here, which is starting here, basically, and kind of going down that way. Now, transition metals do show very great similarities as you go across the period and also down a vertical group. One of the things we probably know about transition metals, right, is if you remember from naming, those are the guys who can have a variable positive charge, right? So that's why we use Roman numerals, right, when we name transition metals. except for 3 that has fixed charges. The 3 transition metals that have fixed charges is zinc and cadmium, which make a +2 charge. And you hang a left there at cadmium and go to silver, it's a +1 charge, right? Everybody else there in transition metal regions can make a variable positive charge. When they form ionic compounds, because they can have multiple oxidation states, a lot of times these guys will end up as the center metal in a complex ion. And a complex ion is a metal in the middle, a lot of times a transition metal, and it has attached to it a bunch of ligands, as we will see. And ligands are Lewis bases. And if you remember, Lewis bases are things that do what? They do donate a pair of electrons. Very good, yes. I had to take a moment to think myself, but I agree with you on that. They do donate a pair of electrons there. And a lot of these guys in the center really are these transition metals as well. So here we go, something like cobalt in the center or transition metal. Each of these ammonias are good Lewis bases. Why is ammonia a good Lewis base? Well, if we draw it there, a little Lewis structure action here. It is a polar molecule with some non-bonding electron pair there on its nitrogen, and it's going to act to donate that. Dare I say, when you get to organic, you may call it something else, but it's the same thing sort of happening in this situation. And in this case, we get a complex ion, cobalt Na3/6 with a +3 charge. +3 charge comes from the cobalt because ammonia is neutral. This is not ammonium, so this is ammonia NH3, and the +3 comes from the cobalt. By the end of this chapter, you will properly name this guy as hexamine cobalt 3 ion. I believe in you. You'll name it. And then we'll have longer names that will just go across the entire screen. And you're like, I need more room. I need more room to name that thing. All right. Well, let's not get too far ahead of ourselves here. All right. So ionic compounds, transition metals. Most compounds do have some different colors depending on the charge of the transition metal and also some of the ligands that are attached. They can absorb visible lights at specific wavelengths. A lot of the compounds are paramagnetic. Paramagnetic means it's like a magnet that's like para. Thank you. Here twice a week for at least a couple more weeks. All right, so it is some unpaired electrons here, yeah? So some unpaired electrons, a little paramagnetic, diamagnetic, paired up electrons. Electrons have spin affected by the electrical field. MS, the spin quantum number, dare I say it? Yes, I remember that vaguely. All right. So let's talk a little bit about electron configuration. As I mentioned a second ago, obviously the transition metals are D block, and as you know, hopefully it starts on 3D, right? And when we look at the periodic table, right there where we have potassium, and then next to potassium is calcium, and then we hit our very first transition metal there is Sc. This is period number 4 on the periodic table. That is N is equal to 4, but this transition metal is actually 3D. Yeah, so remember that the D guys, if you are prone to counting electron configuration off the periodic table, remember the D's are 1 behind the period number. The F's are actually 2 behind the period number, as the F should go up a little bit there in like period 6. And that's actually 4F on the bottom there. Well, not the very bottom, but the second to bottom there. And 5F in that case, and they're actually 2 behind. If not, then as you might remember, there are s orbitals could hold 2 electrons maximum, right? There's p subshells, since there's 3 different of them, they could hold 6 electrons. D subshell, there are 5 of them. Each orbital could hold 2, that's 10 electrons. And F subshell, that's 14 electrons. And if you want to write electron configuration, perhaps you were taught this, maybe not, I don't know. The S's start on the first energy level, the P's start on the second, the D's start on the third, and the F's start on the fourth. At that point, you could just fill in the numbers underneath with the same letters, right? 3S, 4S, 5s, 6s, 7s, 2p, 3p, 4p, 5p, 6p, 7p, 3d, 4d, 5d, 6d, and 5f. And this is the correct order of electron configuration. And you could actually make it pretty quickly yourself. You just remember 1, 2, 3, 4 and go this way. The thing that people screw up all the time is we go 3p and then 4s followed by a 3d. Yeah, so you just kind of keep zigzagging back and around. Remember that the s's, as you can see on the periodic table, actually come before the d's. So again, remember that, or is the order that we go there. So if we were writing something like iron, for example, or actually chromium and copper. Chromium and copper actually are two exceptions to the electron configuration. And that is happening here at the back end. Chromium is 24 and 29 for copper in terms of electrons. And if you followed the zigzag approach there, you would have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. As you may know, right, all the way up to here, that is 18 electrons, which is our shorthand. That is the argon, right? Noble gas configuration that you could write based on the noble gas that comes before whatever you're writing electron configuration from. That's going to be 4s2, 3d4. The exception is here. It's been found experimentally to have one more electron up in the d orbital and one less electron in the s. And that is because when electrons go into the atom, they do go into the s first, and then they start filling the d. And in this case, they're very, very close in terms of energy. So they're very close in energy. So it doesn't take a lot for an electron to get promoted upwards. And what it does in the case of chromium, for example, is it creates a lot of parallel spins, which is really good if you remember when you did orbital diagrams, arrows and boxes, perhaps. You want to maximize the parallel spins, which is why Hund's rule, they call that. Go one at a time and come back and then pair off everybody in the orbitals. And that maximizes our sort of parallel spins. For copper, it's actually the same. It just kind of pairs up everybody up there in the D. As you might also remember, what happens when the D orbitals start getting electrons is there's actually a switch in the energy levels. And what ends up happening is the S's actually end up getting higher in energy after you fill it than our D's. So there's this switch that occurs. And this affects when transition metals lose electrons because of that. When transition metals lose electrons, they lose their s electrons first because they actually end up being higher in energy than the d orbitals. And then if necessary, they can go into the d orbitals and take more electrons out. That's why, depending on your transition metal you're looking at, some of them could have technically upwards of 12 valence electrons, and that's something like zinc can have. By the way, the number of valence electrons for transition metals does equal the group number for transition metals, and that's your 1 through 18 numbering basically as you go through there. And so, for example, there's something in like iron there is group technically 3, 4, 5, 6, 7, and 8. Iron has 8 valence electrons. We'll use them all, never, because we don't have like an iron with a +8 charge or anything like that. And they typically lose 2 and 3 electrons a lot of times. They also, unlike representative metals, right, will not get back to noble gas configuration, which is kind of what representative elements do. When they lose electrons, they back themselves up to noble gas configuration. If you look on the periodic table where chromium and copper is located, and you go down and in, there's a ton of exceptions to electron configuration. Silver is an exception. PD has actually no electrons in the s. They've all been upwards to the d orbitals and stuff like that. So there's a lot of exceptions underneath those guys and in on the periodic table in terms of electron configuration. Most people are just taught to learn those two, but there is a lot more kind of underneath it. Now, as I mentioned before, when they do lose electrons, because of that switch in energy, they do lose the S's first, and that always happens. So we talked about iron there, and iron is number 26 there. Yeah. So if we write our electron configuration for iron with no charge, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6. By the way, this right here is really the 8 valence electrons that iron technically has, the 2 from the S and the 6 from the D. So basically, if we just look at that after the switch occurs, we're going to have those 2 electrons up. And then on our D here, we will have 6 electrons. Again, they do fill one at a time and then come back and pair off. So if we had something like iron with a +2 charge, it has lost 2 electrons. So instead of 26, it has 24 electrons. Once again, it is going to take out these 2 electrons first, and that would give it, I'll just do shorthand here, argon 3d6 would be the electron configuration for iron. If we went to iron 3, it would then be down to 23, which means it still would take out these 2. Then it has to deal down into the D because they're available as well. And we would end up with argon 3d5 in this case. Any questions on that? So transition metals, again, when they lose electrons, we'll always lose the S's first. And then if necessary, we will go down into our D's. That's what we see here. Ti no charge. Ti with a +3 will lose these 2 electrons first. And then we had to take 1 out of the D here to get us to our electron configuration. That'll leave something like iron 3 with 5d electrons, iron 2 with 6d electrons, and something like Ti with a 3+ charge with 1d electron. This is going to be important later on in the chapter when we talk about crystal field splitting and how many d electrons there are. Again, being able to write the electron configuration. Any questions on that there? Let's not do that one. Let's do nickel with a +4 charge. Write the electron configuration for it. Nickel is 28, I think. Yeah. Might just be making up numbers, but I'm hoping for the best there. Okay, so let's take a look. So we'll just start with nickel with no charge is 28. So I'm going to go argon, which is basically 18 electrons. That's going to give me a 4s2 at that point. And maybe I'll count it off there. 1, 2, 3, 4, 5, 6, 7, 8. Sounds good. 3d8. And that again would be nickel with no charge. Nickel with a +4 charge means it's got 24 electrons. So once again here, we are going to take out the 2 S ones first. That's only 2 though. We will then need to come into here and take out our other 2. And that would get us something like argon 4, not 4, argon 3d6 there. Yeah. Any questions on that there? So let's talk a little bit about oxidation states of the first row transition metals. As you can see in red are the common oxidation numbers. Something like Mn is kind of crazy. It's got a bunch of them. But for the most part, +2, +3s are very common. Almost peaks as you get to kind of the midway through the first row, and then kind of comes back down this way. But for a vast majority, +2s, +3s, as we talked about with oxidation states, remember again, depending on what it is attached to or what it may be bonded to, may give you some different sort of charges you may not be familiar with. A couple other important sort of trends, just to remind you, ionization energy is the energy required to remove an electron from an atom in the gas state. And we usually think about ionization energy in conjunction with cations, right? Because when you lose an electron, you become positively charged. So we think about that. As you also know, because you are chemistry professionals, electrons get lost one at a time, right? So something like magnesium will lose one electron. That is what is referred to as the first ionization energy. Then that guy that lost one electron would then dump a second electron out there. And that would be our second ionization energy required to do that. And maybe go a third here and drop one more for good measure. Maybe not. We'll see. Third ionization energy. So every electron comes off. There's a certain amount of ionization energy, which is the energy required to remove it. It is, as you may know, much harder to remove the second electron than the first, right? And the third than the second. And that's because every time we lose an electron, the cation gets larger or smaller. Gets smaller, right? Loses electron cloud, everybody shrinks in. Now these outer electrons are now closer to the nucleus, right? Which means those outer electrons are now going to be held tighter than they were before. It's going to take a lot more energy to remove the next one. And then obviously they're going to get closer again and held tighter and tighter. So that's the trend that you typically see as you go from first ionization energy to second to third. The ionization energy increases as you do that. The first ionization energy trend on the periodic table is it increases as you go to the right on the periodic table and up, and decreases as you go down and to the left in terms of the first ionization energy. That is also what we see, for example, like our magnesium here. To remove the first electron, 735. To remove the second electron gets a little harder, twice the amount of energy to do so, about 1400. And what happens as we jump now to remove that third electron? About, 5 times or so the energy, or maybe something like that. A lot more energy required to do that. That is why when we think about magnesium, we think of it as only having what type of charge? A +2 charge, right? Because it's good luck trying to remove those core electrons, because that's what you're into at that point, right? Once we remove the 2 valence electrons from magnesium, we're now into those core electrons, which are definitely way up on top of that positive charge and can be held a lot tighter. And it's just not energy efficient to do so. That's also why something like aluminum, 580 for the first one, 1800 for the second, 2700. And now look at the jump after you tried to remove the fourth electron. It's about 11,000 from 2000. And that's why when we think of aluminum, it is a +3 charge, because those are 3 valence electrons. Again, you typically do not remove those core electrons. And that's why certain things do have sort of fixed charges, right? So sodium as well, as you can see with sodium, it goes from 495 to 4500. So huge jump, and that's why sodium will only lose its 1 valence electron. Here are a bunch of stuff that clearly you know everything about. But here's our first, second, and third ionization energy, common oxidation states. We also see in terms of melting points, it gets a little bit smaller as we go to the right. Density actually gets a little bit larger as we go to the right. And as we go to the right, the volume in everybody is a little bit smaller, which means density is mass over volume. So we have a smaller number on the bottom and a larger density coming in that direction. Here are dots between our first and third, and you can see a lot more energy there in our third ionization energy to remove the third electron than it is to remove the first. Here's all 3 of them in case you missed the second one in the middle there. You can see it as well. Electron affinity is another trend, and that is a trend of what happens when somebody gains an electron. It is the energy change that occurs when somebody gains an electron, and that is what we usually think about in terms of anions, because those are guys that gain electrons. It is not a perfect trend, but in general, electron affinity is increasing as you go up and to the right, and decreases as you go down to the left. As you can see here in group 7, it increases as you go up, then it kind of comes back down. So it's not a perfect trend, but it is. Electron affinity is the energy change that occurs when somebody gains an electron. It should not be confused with everybody else's favorite, electronegativity, right? And that is the ability of an atom to bring electrons towards itself, right? And electronegativity increases as you go up and to the right on the periodic table and down to the left. The most electronegative element is fluorine, yes. As a Pauling value of 4. Remember 0 to 4, 4 being the most electronegative, 0 not so much. Change in electronegativity value, subtract them, gives you whether you got a polar bond, non-polar bond. Feel like it's too much 200A right now.